So first of all, thanks for this opportunity to the organizers. So my talk will be a bit different from previous two talks. So I will be talking on effect of peculiar velocities on cosmic bispectrum, and will show my recent results, which I have done with my professor Bharadwaj on the reionization bispectrum redshift space. So to understand the large scale structure of the universe, we study distribution of various tracers. Here I have shown two of them, the typical distribution of galaxy from galaxy redshift surveys, 2D of galaxy surveys, and each point here shows the one galaxy. And what we record is the redshift and angles of galaxies. And on the right hand side, I have shown the H1 distribution during epoch of reionization, and these maps show the brightness temperature fluctuations. So to extract cosmological information from these observations, we have to do statistics. So summary statistics is one of the key things we do, and power spectrum is one of these summary statistics which we use to exploit the cosmological information from these observations. And this power spectrum is sufficient if our underlying distribution is Gaussian distributed. But the late time evolution of universe is highly nonlinear and highly non-Gaussian. So we need to go to higher order statistics to extract maximum information of these from these observations. And this epoch of reionization is also highly non-Gaussian process. So bispectrum is the lowest order statistics which captures the non-Gaussianity of these underlying distribution. And this is defined as the ensemble average of product of fluctuations in Fourier space corresponding to three different K modes which form a closed triangle. So bispectrum is a function of closed triangle in a Fourier space. So if universe is isotropic, then the statistics do not depend upon the orientation or of these K modes. So the direction of these K modes do not affect our statistics. So we can only use the magnitude of these K modes to understand the statistics. So bispectrum, which is a function of closed triangle, is independent of orientation of triangle in the K space, if in the isotropic space. So we can use only three parameters to find the shape and size dependence on the bispectrum. So you can use any of them. So I have labeled these K1, K2, K3 such that K1 is largest side of triangle, K2 is second largest, and K3 is smallest side of that triangle. And so we define our three parameters as K1, which is the largest side of triangle, mu, which is the angle between largest and second largest side of triangle, and T, which is the ratio of between these two. So why we are using this complicated terminology here? So the thing is, we can parameterize size of triangle using this K1 and shape of all triangles using these mu and T parameters. So if for a fixed K1, for a fixed size of triangle, if the each point in this mu T space, so here it is the x-axis is mu and y-axis is T, in this mu T space, which I call shape parameters, each point here shows the different shapes of triangle. So for example, here this point shows corresponds to equilateral triangles, and this line shows the L isosceles triangle. The two largest sides are same. This shows the squeeze triangle limit, and here is the linear triangle and stretched triangles. So we can study the shape dependence of bispectrum using these parameters, which are very convenient. So the details are in this paper. So, but the tracers we are talking about are observed in redshift space, not in real space. What that means is the observations of, for example, galaxy surveys, we observe only redshifts and angles of these galaxies. But to do statistics, we have to map out these galaxies in a 3D box, and for which we need real distances of these galaxies from us. And to calculate these real distances, so we use this formula, and we use the redshift that we have calculated of these galaxies to find out the distances of these objects. But this redshift is not solely due to the Hubble expansion of the universe. There is also contribution from peculiar velocities of these objects and due to Doppler shift of the objects. So the overall effect of this thing is the distribution will be distorted along the line of sight. Professor Kaiser had pioneered work in this thing. So, for example, if a object is here in the real space, shown in green line, and any observer is seeing this object along this line, and it is going away from observer with Hubble velocity, and it has some peculiar velocity component in any random direction. I have chosen this. So we will end up placing this object at red point instead of green point, which is its original position. Okay, and this offset will be decided by the line of sight component of this peculiar velocity. So the overall effect is we will see the distribution a bit squashed along line of sight. It can be squashed or elongated depending upon the scale we are talking about. So the crux of the story is the now statistics also depend upon the angle between the line of sight and k vector. So now your statistics also depends on the direction of the k modes along the line of sight direction. So the power spectrum, which is the lowest order statistics we study, has been extensively studied by decomposing it into the legendary polynomial basis, and so we can study the effect of these anisotropies on power spectrum by decomposing it into this legendary polynomial. Similarly, in bispectrum case, which is the function of closed triangle configuration, we also need to take into account the angles of these three modes with the line of sight direction. Okay, so it has been found that the isotropy is broken along the line of sight direction, but there is still a rotational symmetry on the plane perpendicular to the line of sight. So any rotation that changes the triangle on the plane perpendicular to the line of sight does not affect bispectrum. So using this rotational symmetry on the plane perpendicular to line of sight and closed triangle condition, we require 5 parameters to specify shape, size, and orientation of triangle. Okay, so people use Euler angles or so on. There are many parameterizations, and so similarly to the case of power spectrum, we can study the anisotropy of bispectrum by decomposing it into the spherical harmonic basis. So there are many works on that. I am choosing this thing from this paper. So so this BLM is called the multipole moment, and for a given shape and size of triangle, we can calculate multipole moment, which captures the orientation dependence of bispectrum for a given shape and size, and we can exploit this multipole moment and extract cosmology from that. So for a given shape and size of triangle, we can implement this in our algorithm to find out the multipole moments. But I am doing this thing right now. So for m, for any general m value, so L and m are the these multipole moments I am talking about. For a general m value, it is very difficult to implement this. I am doing right now. But for m is equal to 0 multipole moments, it's very easy because it just boils down to the expansion in terms of legendary polynomial, which was in case of power spectrum. So for now, I will show you the results for hydrogen 21 centimeter bispectrum during epoch of reionization and how redshift space distortion affects these results. For whom those who are interested, I used RIA Yuga and simulated the epoch of reionization hydrogen distribution using these parameters, which are not important. So the main thing is we simulated at 6 different redshifts, which we assume at 13 epoch of reionization started, and at 7 the epoch of reionization was nearing its end, and we generated 5 realizations of each at each redshift to calculate the statistical significant result, and this was done with my colleague Suman Pramanik. So this here I just want to give you an idea how this looks like. So this is the brightness temperature fluctuations at initial stage of epoch of reionization at redshift 30, and the neutral fraction was 0.99 there in our simulation. And as epoch of reionization progresses, we can see the universe is getting reionized from the regions where galaxies are there, and at higher and higher redshift, at lower and lower redshifts, it's going more reionized. So this is the end point of our epoch of reionization, which we are taking at redshift 7, and neutral fraction is 0.15. Okay, so this is the result what we got. So first row is the real space bispectrum, which is just a real space bispectrum of this thing, and second row is the second and third row is the redshift space bispectrum. This is the monopole of that redshift space bispectrum, and this is the quadrupole of redshift space bispectrum. All right. So and this first column. So we did this analysis for squeezed, stretched, and equilateral triangle for 3 different triangle shapes. And first is for squeezed triangle, second is for stretched, and the third column is for equilateral triangle. And different lines here, different colored lines shows the different size of triangle. So basically this plot shows the real and redshift space bispectrum at corresponding to 3 different shape of triangle and 4 different sizes of triangles. Okay, the first thing we note here is the squeeze triangle has the largest value of bispectrum, and bispectrum is positive at the starting point of epoch of reionization. So
Interestingly, we find that the bispectrum, the non-Gaussianity, is driven by matter fluctuations in the initial stages of epoch of reionization. So here these dashed line shows the only matter bispectrum. So no epoch of reionization is here. So these dashed line are just the matter bispectrum from second order perturbation theory. And we can see that most of the lines follows the matter bispectrum. So the epoch of reionization follows the matter fluctuations at the starting point of epoch of reionization, and these results were also quoted in some previous works done by Dr. Suman here. So as epoch of reionization progresses, the bispectrum, so these bispectrum deviates from the matter fluctuations. Okay, so this matter bispectrum goes somewhere else, and the epoch of reionization bispectrum deviates from this. And so the non-Gaussianity due to H1, neutral hydrogen fluctuation, dominates as epoch of reionization progresses. So basically, non-Gaussianity is driven by matter fluctuations at initial points of these epoch of reionization. Then it deviates, it becomes negative, and and because this is a signature of epoch of reionization, the bispectrum becomes negative, and the fluctuations are dominated by H1. So the magnitude increases as we go to the higher epochs, and the bispectrum is large. Bispectrum at large scale becomes negative first. So this is very a good feature, that bispectrum, the sign change of bispectrum depends on the size of triangle. So for a small k value or at large scale, bispectrum becomes negative first, then at another next higher k value, then next higher k value, and for a large k value at small scales, bispectrum never becomes negative. So that means these fluctuations are at higher k values are still dominated by matter fluctuations, and at small scales maxima shifts to so this basically becomes maximized for small k value when the neutral fraction is 0.5. So when half of the universe is reionized, half of the universe is not reionized. So this is the, okay, so I will skip over it. So how a redshift space distortion affects it? It increases the magnitude, overall magnitude of bispectrum at all the scales, and sign of this bispectrum also changes. And the large effect of the redshift space distortion is at the large K1 values. And for small K1 value, effect is at the high redshift, because there the matter fluctuations were dominated. The main point is this
At this K1 value, for example, 1.18, the bispectrum was negative at some epoch in real space, but in redshift space, it never goes to negative. Okay, and because this is due to the matter fluctuations dominate, and for the lower values of K1, so for lower value of K1, so it remains positive for longer time. So here it becomes negative at earlier epochs, but now it's becoming negative at later epochs. So the epoch of sign reversal changes. We also calculated the quadrupole moment. So it's very statistically significant. We have done it for first time for epoch of reionization. We are so this work is under process. So the quadrupole moment is very similar to the monopole moment. So we need to take into account higher order moments also if we want to study this to study the epoch of reionization. And okay, so that's all. I will skip over that. So this is the shape.
If you could summarize.
So that's the conclusion. I will leave it you with that.
So thank you, Sukhdeep. So if anybody has questions.
So I guess all these changes in shape with redshift and scale, what does it mean is like this, that the bias of this field is changing quite a lot during this process, right? Because I mean, you got the matter power spectrum, the matter bispectrum, and then the H1 bispectrum was very different, goes to negative. So I think that's a clear indication that bias parameters are changing.
No, so actually in this analysis, for example, we are showing this real space and monopole moment. So here, this is just a field. So we have a field we generated in the real space, no redshift space distortion. We simulated the similar field with the redshift space distortion. Now there is no theory, no matter, no like I don't know. So if we just simulated this with redshift space distortion and we saw that, so the epoch where it becomes negative and positive changes. But the thing with bias, I don't know. I have to think about it actually.
Maybe you could discuss it during lunch.
Yeah, exactly.
So if anybody, so if no questions are there, like, so let's thank the speaker once again.